Hi, my name is Peter Schwartz, and I've created the WaveBot for my final project. We have some of my prototypes, earlier prototypes here on the right, and on the left, we have an actuated prototype. So we have Theo Jansen's Caterpillar robot here on the upper right. This is a continuous wave movement. It's propelled by the wind, and the friction between it and the sand actually creates this wave movement. I'm trying to reverse this process, create the wave movement, and therefore forward propulsion. So on the lower right, you can see my 3D printed flexible TPU prototype, diamonds connected at the horizontally facing points. And what I'm trying to do is just manipulate the parallelogram, which is the beams and the diamonds at the beginning and end of each period. I need 2 full periods to create 2 points of contact at all times, whether that's at the top or the bottom of the robot. And I can actuate this in a number of different ways that I'll explain further. So there are 4 axles that pass through the body and secure the beams, 2 pins at the end of each wave, and this really constrains the movement and actually prevents oscillation back and forth, lets the wave pattern travel down through the body of the robot. And still in the lower right, we see the 2 simple beams just connecting the axles. In the upper right, we see the driving beam attached to the servo and the driven beam attached to the motor arm. This just changes the angle of the parallelogram and creates the wave movement. There's always a tab for manual actuation as well. It's compressible in the X and the Z direction. It's an under-actuated system. A single actuator creates a continuous movement. And what I call the feet or the tips of the diamonds are always moving in the same direction when extended outwards. When they're retracted inwards, they're moving in the opposite direction of locomotion, but can't actually contact the surface. So we have here on the right, what I have here, the angle of the diamond. That angle multiplied by the number of diamonds has to be less than 180, or else this robot will actually buckle and won't work accordingly. In the upper right, we have these 2 slightly staggered circles, and you can see the red body is actually never traveling over 180 degrees along each circle. Manufacturing, again, this is 3D printed. I use NinjaFlex Cheetah TPU. It's a very flexible TPU. I have a direct drive fan upgrade setup to reduce stringing and clogging. 20 kilogram, 180 degree high torque servo motor provided plenty of power, 2mm stainless steel rods. And a future product would be a TPU mold and a dragon skin body. Also, I would like to use EcoFlex McKibben actuators and capacitive sensors from, again, a TPU mold. This future design, these capacitive sensors would attach the axles and the pins, and they're stretched depending on the angle of this parallelogram. And the McKibbens would then be actuated depending on how the parallelogram needs to be actuated. So at this point, the top capacitive sensor is stimulated, and then therefore it would actuate the McKibben going from the lower right to the top left. I'd also like to add in a Raspberry Pi Zero to control this system in the future. And we have, I initially tried a constant curvature model, but realized quickly that these diamonds themselves are not bending, they're bending between each diamond. So I found that a sine pattern actually simulated this best. So you can see that in the lower left, this animation here. And in the top, this is really what needs to be actuated. As long as this movement can be actuated, the robot will go through each period between each of these diamonds. And then we have here on the bottom, every diamond throughout the robot is doing the same movement. It is rotating at the top and bottom. So right here, the robot pushes the robot to the side, and it can do the same thing at the top as well. SolidWorks finite element analysis here, I created these parameters based on the anisotropy and layer adhesion issues of 3D printing TPU, but it looks like it can handle this load. This is 1 Newton force at each point. I would like to run a fatigue analysis in the future though. We have a couple of videos here of manual activation here on the left. As you can see, the pin is hitting the top and bottom beams, and this actually lets this wave travel to the left. So this robot would be traveling then to the right. Then we have an actuated robot on the right. As you can see, a little too much torque, and these beams are not strong enough. So they're bending, and the pin is actually not able to do what it should. A few of these challenges, a lot of stringing on these, what I call feet. And I'd like to, it really inhibited the movement of this robot. So that's why I would like to use dragon skin in the future. And as you can see, the pin didn't always work, and these beams need to be more rigid. So a broader impact here, we're looking at disaster exploration, pipe inspection. This robot can get crushed and keep moving. Miniaturization can move throughout the body in that digestive system or through veins and arteries, but it can really travel vertically upwards in a pipe as long as that pipe is as big or slightly smaller than the robot. So So thank you very much.